You know, in chemistry, actually making something is really just the beginning. The real question, the one that matters, is how well did you make it? So in this explainer, we're going to break down the two key ways chemists figure out if a reaction is a true success, from what happens on the lab bench all the way to the company's bottom line.
So, you've run a reaction, you've got your product, awesome. But was it a good use of your time, of your materials? Was the whole process efficient? Or was it actually kind of wasteful? These are the really important questions we're going to tackle today. All right, so we're going to go on a little journey here. We'll start with a hands-on experiment, the kind you do in a real lab, and then we'll connect that all the way to the big picture stuff, the things that affect manufacturing costs and even our environment. This quote just nails it, doesn't it? It perfectly captures the two sides of the coin for a successful reaction. First, how much stuff did you actually end up with? And second, how smart was your recipe? How well did you use your ingredients? We're going to unpack both of these, starting with the practical side of things.
Okay, let's head over to the lab bench and see how this all works. To get the numbers for our first measurement of success, we need to do a procedure that is all about one thing: precision. It's called a titration.
A titration is just a super accurate way to figure out exactly how much of one chemical you need to completely react with another. The best way to think about it is like baking. You've got your dry ingredients, and you carefully add the wet ingredients bit by bit until that dough is absolutely perfect. That's what we're doing here, but with an acid and an alkali.
As you can see, the whole process is obsessed with being precise. You use a special tool, a pipette, for an exact measurement of your alkali. You add an indicator that'll change color at the perfect moment, and then you use this long glass tube, called a burette, to add the acid literally drop by drop. You even do it a few times just to make sure your results are spot on.
And all that careful work gives you a data table that looks something like this. You usually do a rough one first to get in the ballpark, and then you focus on the results that are super close together. We call those concordant. See here? Runs 1 and 3 are almost identical. We just average those two, and we get our final ultra-accurate volume, 23.75 cubic centimeters. That is the number we were looking for.
And of course, because this is a real lab procedure, safety is everything. You're working with chemicals that can be irritants, so things like gloves and eye protection are totally non-negotiable. Okay, so we've got our data, we've been safe, now what do we do with it?
All right, now that we have our measurements, we can calculate our first measure of success. It's called percentage yield. Think of this as your practical report card. It's all about comparing what you actually made to what you could have made in a perfect world.
Let's break this down. On one side, you have the theoretical yield. This is your plan. It's the absolute max amount of product you could possibly get if everything went 100% perfectly. But on the other side, you have the actual yield. This is the real deal. The stuff you can actually hold in your hand at the end. And trust me, in the real world, you might lose a little bit when you're filtering, or maybe the reaction just didn't quite finish.
And the formula to figure this out is beautifully simple. It's just your actual real-world result divided by your perfect world plan, and then you multiply by 100 to get a percentage. This number is like a direct grade on how well you, the chemist, actually carried out the experiment. So, for example, let's say your calculations told you that you could make 2 grams of product, but at the end of the day, after you filter and dry everything, you only have 1.6 grams. Well, that means your percentage yield is 80%. And hey, in a lab setting, 80% is actually pretty good.
But here's the twist. A high yield doesn't tell the whole story, not even close. So now let's move on to our second metric, atom economy. This has nothing to do with your skills in the lab. This is all about the quality of the chemical recipe you are using in the first place.
Atom economy asks a much more fundamental question. How much of your starting ingredients, the actual atoms, ended up in the thing you wanted to make? Anything else is just waste. It's like baking again. How much of your flour, sugar, and eggs ends up in the cake versus how much gets tossed out like the eggshells?
Take a look at this reaction from making hydrogen gas. We mix methane and steam. Our goal, the whole reason we're doing this, is to get the hydrogen. That's our desired product. But look, the reaction also spits out carbon monoxide. In this case, that's just a wasteful byproduct. Those carbon and oxygen atoms didn't end up where we wanted them. And here's how we calculate it. We take the total mass of all the atoms in the product we actually want, and we divide it by the total mass of all the atoms we put in at the very beginning. This tells us, right from the chemical blueprint, how efficient or wasteful a reaction is by its very design. This chart makes the problem with our hydrogen recipe painfully clear. That big bar on the left, that's the total mass of all our starting ingredients. And that little tiny bar on the right, that's the mass of the hydrogen we actually wanted. You can see right away just how much of what we started with is going to waste.
Okay, now for the big reveal. Imagine you're an absolute rock star chemist. You run this reaction to make hydrogen, and you get a stellar 95% yield. You perform the procedure almost perfectly. You should be proud, right?
Well, yes and no. Because look at this. The atom economy for that very same reaction is a terrible 17.6%. And this is the key idea. You can perfectly execute a fundamentally wasteful recipe. Your lab skills were A+, but the chemical blueprint itself was designed to throw away over 80% of your starting materials.
So why do we care so much about both of these numbers? Let's zoom out and look at the bigger picture to see why this isn't just an academic exercise. In the real world, in industry, the perfect reaction is one that has both a high yield and a high atom economy. When you have both, it means you're not wasting money on expensive raw materials, it means you're producing a lot less waste, which is obviously better for the environment. It all leads to more sustainable and way more profitable chemical processes. And that leaves us with this final thought to chew on. What really defines success in chemistry? Is it the amazing skill of the chemist who gets a high yield no matter the reaction? Or is it the genius of the chemist who designs a reaction with a near-perfect atom economy from the start, ensuring almost nothing is wasted? The real answer, of course, is that you need both.